Hello everyone, my name is Nidhi Chauhan. I am assistant professor in Suresh Gyan School of Pharmacy, that is a part of Suresh Gyan University, Jaipur. Today we are going to discuss about the topic that is your carbonyl compound. It comes in your pharmaceutical organic chemistry first, that is in your second semester syllabus, B.Pharm second semester syllabus, or you can say B.Pharm first year. So the learning objective of our topic, today's topic is that what are the, here we are going to study about the ketones, and also we are going to study about the method of preparation of ketones and aromatic ketones, and how the ketones are prepared in your industrial scale or your laboratory scales. Similarly, the aromatic ketones, how they are prepared in uh, industrial or in the laboratory scale. So here we are going to discuss this: what are the ketones, what are its nomenclature, and what are the method preparations of the ketone and aromatic ketones, and what are the structures of ketone. So the student outcome, they will going to know about what are ketones, and what they will also learn about the preparative method of ketone. So the introduction, that is that in chemistry, a ketones alkanon are an organic compound with the structure RCO, where R dash, where R and R dash can be a variety of carbon containing substituents, and structurally the ketone carbon is often described as sp2 hybridized, a description that includes both their electronic and molecular structure. Ketones are trigonal planar about the ketonic carbon with CCO and CCC double bond angle of approximately 120 degrees. So these ketones that are also known as alkyl and bi, because alkyl group is attached to this ketone, and ketones in nomenclature we are suffixing this name on was suffixing on this alkane. E is replaced by this on. That is why they are also known as alkanone. And these are the organic compounds that is having the structure RCOR. So here two alkyl groups are attached to this ketone, and these two alkyl groups can be your alkyl groups, or these R can be your alkyl groups, or they can be your aryl groups also. If aryl groups are present on this R, in place of this R, then it is a aryl group, that is a aromatic, and if R is alkyl groups are present in this alkyl R position, then they are the aliphatic ketones. So here, where R and R dash can be a variety of carbon containing substituents. So here they are can be a these they contains a carbon. So these can be a carbon containing substituents. So structurally, the ketone carbon is often described as sp2 hybridized. So these ketonic carbons, these are described as your sp2 hybridized. So these carbons that are attached to these alkyl groups and your oxygen atom, that carbon is your sp2 hybridized, and the description that include both their electronic and molecular structure. So in this figure, you can also see this, and the ketone are trigonal planar around the ketonic carbon with CCO and CCC bond angle of approximately 120 degrees. So here you can see that the carbon and the oxygen is having the pi bonding. That is why here the pi and pi bonding are overlapping, and they are forming a double bond between the C and the carbon bond, or C and the oxygen. And this R is also a sp3 hybrid R group, because this carbon is also connected to the three hydrogen atom and one carbon atom. That is why these are also the sp3 hybridized. And but the carbon that is attaching with this oxygen and the two alkyl groups, they are also they are the sp2 hybridized carbonyl carbon, because this carbon is bonded to two alkyl group and one oxygen group. And according to the hybridization, the number of atoms that are attached to this atom and the number of lone pair that is present, the addition of both. So here the number of alkyl groups that the number of atoms that are attached to this carbon is 1, 2, and 3. That is why it's hybridization is sp2 hybridized, and the R that is attached to this carbon atom, that is attached to the four atoms. That is why this carbon that is attached to this four atom, that is why this is having a sp3 hybrid R group. And this oxygen is also having the sp2 hybridized oxygen, because oxygen in at one place it is bonded to the carbon atom, and it is having the two lone pair that are present on the oxygen atom. That is why it is having the sp2 hybridized oxygen atom. Next, basic skeletal structure of carbonyl group in ketone is same as in aldehyde. So these um, skeletal structure of this carbonyl group in ketone is same, means it is having the same carbonyl group of this ketone is same as that of an aldehyde, and it is in planar. This is the structure of this ketone, and it is in a planar stage, and it is similar as that of your as the skeletal structure is same of this ketone is similar as in aldehyde. Next is the nomenclature. So here the common name of ketones are named on the basis of alkyl group attached to the carbonyl group. So the name of the ketones are named according to the or on the basis of the alkyl groups that are attached to the carbonyl group. So the IUPAC nomenclature. So in IUPAC nomenclature, the ketones are designated by suffixing on. So here on is designated on this ketone. So prefix is the name of hydrocarbon. So the prefix that we will use here alkanon. So here longest hydrocarbon chain containing carbonyl carbon is selected and named it by substituting E of alkane with 1. So here we have to first see that which is the longest hydrocarbon chain, and it should contain carbon, so containing carbonyl carbon is selected. So containing carbonyl carbon is selected, and it is the longest carbonyl, it is the longest hydrocarbon chain which is having the carbonyl carbon also is selected in that longest chain, and we can name it by substituting the alkane. From the alkane, we have to substitute this E. E is replaced by this on. So here this E is replaced by this one, then its name is alkanon. So here by the numbering the chain, lowest number is given to the carbonyl group. So while numbering, if we are numbering the longest carbon chain, then we have to number the carbonyl group the lowest one. It means that we have to number it first. One is the lowest number, so we have to name first the carbonyl carbon. After that, we have to name the other carbon. So from there, the numbering will start. Other substituents are numbered, named, and placed as prefixes in the alphabetic order. So if other substituents are attached to this carbon chain, long carbon chain, then we have to use the prefix of that substituent that are attached in alphabetical order. So if there are two carbonyl group in a molecule, it is named as alkane dione. So here, if the two carbonyl group, it means two ketone groups are present, or you can say the two carbonyl group, that is your C double bond O, is present in a chain two times, then we have to name it as alkane dione. So here you can see here the example is given, that CH3COCH3. So here we have to number it from any side. So its name is your dimethyl ketone, or you can say it acetone. So here its name is your dimethyl ketone, because the two dimethyl groups are attached to the methyl groups are attached to this carbonyl carbon, and we have named it dimethyl ketone. Or in the simple or the common, it is named acetone. According to the common system or trivial system. Next is your the CH3CO, CH2, CH3. So here this is your ethyl methyl ketone, because on one side it is your ethyl groups or ethyl group is attached, and on the second side methyl group is attached. So here ethyl methyl ketone means here that the ethyl on one side is attached, and on the other side methyl ketone, then ketone is on the between. So here ketone should be used in the suffixing name. So here this name is ethyl methyl ketone. Again, this nomenclature, that the name of common name of IUPAC is named according to the alkyl group that is attached to the carbonyl carbon. But in IUPAC system, the nomenclature ketone are designated by suffixing on. So here, this is your common name that we have used. So here the IUPAC, in according to the IUPAC name, IUPAC nomenclature, the ketones are designated by a suffixing on. So here we have to use alkanon. So here the name should be alkanon. So here, longest hydrocarbon we have to see. We have to select the longest hydrocarbon chain that is containing carbonyl carbon, and we have to substitute it E by the alkane with on, and we have, while numbering the chain, while we are giving the number to the chain, firstly we have to give the lower number to this carbonyl carbon. Then the other substituents are numbered accordingly. After that, the other substituents are made numbered, and there is a, we have to prefix our alphabetical order. So here we have to use that other substance that are attached to this long chain. Then we have to number it accordingly, and then we have to prefix its in a alphabetical order. So if there are two carbonyl group in a molecule, it is named as alkane dione. So if there are two carbonyl groups in a molecule, it is named as alkane dione. So here CH3, COCH3, this is according to the common name, because here we have used that in the common name we have to name it according to the alkyl group that is attached to the carbonyl group. So here the alkyl group that is attached to the ketone group, that is why its name is your dimethyl ketone, or you can say acetone. So here its name is CH3CO, CH2, CH3, ethyl methyl ketone. These names are according to the common system. So this is according to the IUPAC system, that CH3, CO, CH2, CH2, CH3. So its name is your 2-pentanal, because on the second position the carbonyl compound carbonyl group is attached. That is why its name is 2-pentanal, and it we have numbered it from this side, from the left side. So CH3 get the first position, then CO, then CH2, then CH2, then CH2. So according to the IUPAC, its name is your 2-pentanal, and according to the common system, its name is 1, 2, 3. That is your propyl methyl ketone. Next is your CH3, CH2, CH3, COO, and CH3, CH. So here we will start the numbering from the right side. So here the carbonyl group is present on the second position. So 1, 2, 3, 4, 5, 6. So on the fifth position, there is yes, on the fifth position there is your methyl group, plus on the second position also there is a methyl group is present. That is why we will name it 2 and 5 dimethyl hexane 2 hexanon. So its name is 2,5 dimethyl hexanon, and the next its name is 1. Here we will start numbering from the left side. That is your CH3, CO, CH2, CO, CH2, CH3. So here we name it 1, 2, 3, 4, 5, 6. So here its name is 2, 4 or 2, 4 hexa, 2, 4 hexa dine on, because here two groups are present. That is why we are using here di word. So dione, hexadione. Next is your polarized CO bond. Electronegativity is C 2.5, and the oxygen is having the electronegativity that is 3.5. It makes carbon partially positive, which attract negatively charged nucleophile. Here electrons from HOMO of nucleophile move to LUMO of electrophile, that is C of C double bond O group. So here the polarized C double O bond, that is having the carbon is having the electronegativity that is 2.5, and oxygen is having the electronegativity that is 3.5. That is making the carbon partial positive, positively charged, which are attracting the nucleophile, which are attracting the negatively charged nucleophile. Nucleophile have the capability to donate electrons, so they will donate electrons because this carbon is positively charged because it needs electron, and the oxygen is your partially negative charge because it is more electronegative than this carbon. That is why it will attract electron from this carbon atom, and the carbon will get the partial positive charge and the oxygen will get the partial negative charge. So this partial positive charge carbon will attract the electrons, attract the negatively charged nucleophile, and these nucleophile will, the electron from this HOMO of this nucleophile will move to the LUMO of the electrophile. So here the nucleophiles are moving towards the carbon of carbonyl group, C double bond O group. The newly formed sigma bond that are converting this sp2, converting this trigonal sp2 hybridized carbon atom of carbonyl group to tetrahedral sp3 hybridized state attack of nucleophile is at approx 107 to the degree to the C double bond O bond, and any part of molecule that causes steric hindrance to this will reduce rate of addition and acid and base catalysis of carbonyl carbon in a nucleophilic addition reaction has been discussed in aldehyde unit. So here we have to form. So here the newly formed sigma bond. So sigma bond here is converting it into the trigonal sp2 hybridized carbon atom, and this sp2 hybridized carbon atom of carbonyl group to a tetrahedral sp3 hybridized state that will attacking the nucleophile is at approx 107 degree to the C double bond O. So here this trigonal sp2 hybridized carbonyl group carbon is transforming, or you can say it is converting into the tetrahedral sp3 hybridized state by the attack of the nucleophile on this carbon atom of the carbonyl group, and it is at approx 107 degree to the C double bond O bond, and any part of molecule that causes steric hindrance to this will reduce rate of addition. So here that any part of molecule that causes this steric hindrance, if there is a steric hindrance in this molecule, then this will reduce the rate of addition. Means it will reduce the rate of nucleophilic addition to this molecule. So the acid and base catalysis of carbonyl carbon in nucleophilic addition reaction has been discussed in the last unit, which we have discussed about the aldehyde. So here the sigma bond that is formed between the carbon and the nucleophile, that is converting the trigonal sp2 hybridized carbon, that is converting the carbon that is involved in the C double bond O to the tetrahedral sp3 hybridized, because after the attack of the nucleophile to the carbon atom, or there is a formation of the sigma bond between the carbon and the nucleophile, which is at an approx angle at 107 degree to this C double bond O. So here if the molecule is causing any steric hindrance, then there will be a reduce of this nucleophilic addition reaction. So here there will be a reduce in the rate of addition or in the rate of nucleophilic addition reaction. The acid and base catalysis of carbonyl carbon. So in the nucleophilic addition reaction, we have discussed in the aldehyde unit. So here synthesis of ketones. So next is the synthesis. Like aldehydes, like we have studied the synthesis of your aldehydes. Similarly, ketones are also prepared and synthesized by the number of methods. Some of these are discussed here. First is your oxidation of secondary alcohol. So here we are oxidizing the secondary alcohol with this K2Cr2O7, or we can also oxidize with this MnO2 or chromium anhydride in acidic medium, and this yields our ketone. So firstly, secondary alcohol is giving you ketone with the same number of carbon atom as the original alcohol. And this firstly secondary alcohol give the ketone with same number of carbon atom as the original alcohol. However, prolonged treatment with oxidizing agents produces a mixture of acids containing fewer number of carbon atom than the original alcohol. So here we have this alcohol is oxidizing in the presence of your K2Cr2O7, that is your potassium dichromate, and this is converting and it is forming this ketone. This is forming a ketone. So after that, this alcohol is again oxidizing in the presence of potassium dichromate, and it is converting it into the this ketone. So this is a ketone that is formed from the oxidation of the alcohol, and it can be occurred in the process in the presence of this oxidizing agent, that is your potassium dichromate, or we can use here MnO2, or also we can use a chromic anhydride in the acidic medium, and after that we can yield our ketone. So here firstly secondary alcohol gives ketone with the same number of carbon atom as the original alcohol, and after that the prolonged treatment with oxidizing agent produces an acid. If we are using a oxidizing agent, if we are using a prolonged we are giving this ketone a prolonged alcohol prolonged treatment, then this is converted into your this will give you acid, and containing fewer number of carbon atom than the actual original alcohol. So the tertiary alcohol are resistant to oxygen. Oxidation is neutral or alkaline media, but they are oxidized in acidic media, resulting in formation of mixture of acid and ketone, and each contain fewer number of carbon atom than the original molecule. So this tertiary alcohol is not resistant. So this tertiary alcohol is resistant to the oxidation, and this oxidation in neutral or alkaline medium, but they are not oxidizes, but they are oxidized in acidic media. But they are oxidized in acidic media. So the tertiary alcohol can be oxidized in the acidic medium, but not in the neutral or the alkaline media. And this acidic media, and this results in the formation of a mixture of acid and ketone, and this contain fewer number of carbon atom than the original alcohol. So the alkaline KMnO4 is also an oxidized agent. So this alkaline KMnO4 is also used as oxidizing agent. Next is by open air oxidation. So it involves a special reagent, that is your aluminium T butoxide. So this special reagent, that is your aluminium T butoxide, CH3 CO 3 Al, that is aluminum T butoxide, that is refluxed. So here we are refluxing it with the secondary alcohol, and the acetone cyclohexanol is used as a solvent. So here this aluminium T butoxide is acting as a oxidizing agent, and acetone accepts hydrogen as hydride ion from secondary alcohol. So here you can see the alcohol, that is your secondary alcohol. It is treating in the presence of this acetone cyclohexanol, and plus this aluminium butoxide T butoxide is reacted, and there is a formation of this ketone, and this alcohol is also formed here. Now the mechanism of here, you can see here exchange reaction to take place. So here alcohol and this aluminium butoxide is reacting, and there is a formation of this alcohol, that is your tertiary alcohol, and here you will see this is a complex that is formed. So here exchange reaction take place. After that, in the step second, you will see that new complex is formed. This acetone is reacting with this aluminium T butoxide, and there is a formation of this complex is formed here. So you can see here the complex which is formed from this acetone and aluminium T butoxide. In the step third, you will see this complex that is formed. It will form the molecule of this molecule of acetone is formed. So similarly, 2 more moles of acetone will react with above 1 mole formed complex and give two more moles of ketone product. So if there is a two more molecules of this, you have seen here that the two more molecules of this ketone is reacting with this above 1 mole. They are forming a complex and they are giving the two more moles of ketone product. Next is your similarly, two more moles of acetone will react with above 1 mole formed complex and they give two more moles of ketone product. So here, if the two more moles of acetone is react with this 1 mole of the complex, you can see the 3 moles we have taken here, 3 moles of acetone and this aluminum butoxide, we are reacting with this butoxide, then there is a formation of this ketone molecule and 3 moles of this complex is also formed here. The reaction is useful as for oxidation of polyfunctional compound as this reaction condition are mild. So this reaction condition are mild. For example, in unsaturated alcohol as its reagent does not affect double bond. So primary alcohol can be oxidized by this aluminum p-butoxide if in acetone is replaced by p-benzoquinone as it is better hydrogen acceptor than acetone. If the acetone is being replaced by this p-benzoquinone, then this primary alcohol can also be oxidized by this aluminum p-butoxide. Next, by the heating calcium salt of any monocarboxylic acid other than formic acid, ketones are formed. So if we are heating this calcium salt of a monocarboxylic acid with this other than formic acid, then there is a formation of the ketone. So this is the calcium salt of the monocarboxylic acid, and this is forming a ketone here, and the calcium carbonate is also formed here. The fourth reaction is your when vapors of any monocarboxylic acid except formic acid are passed over manganese oxide at 300 degrees centigrade, then ketone is obtained. If the vapors of this monocarboxylic acid is are passed, we are passing this vapors of the monocarboxylic acid over the manganese oxide at 300 degrees centigrade. At 300 degrees centigrade, we are passing the vapors of any monocarboxylic acid over this manganese oxide. Then the ketone is obtained here. So RCOOH is reacting in the press, or we can say that it is passing over this manganese oxide at 300 degrees centigrade. Then the ketone is formed. Plus carbon monoxide plus H2O also formed here. So the mixture of monocarboxylic acid yields mixed ketone. So here the mixture of this monocarboxylic acid, they are forming a mixed ketone. So these are forming a mixed ketone plus CO2 plus H2O. So here the mixture of this carboxylic acid, the mixture of the monocarboxylic acid are also passed over this this manganese oxide. Vapor of this are passed over this at 300 degrees centigrade. Then the mixture of this, then there is a formation of ketone plus CO2 plus H2O formed. Besides this, the RCOR and R2COR2 are also obtained. R dash CO, R dash and R2 CO, R dash are also obtained. So from ketone, from alkene, ketones can be prepared from alkene as follows. So that is first reaction is the ozonolysis. So ketone can be also prepared from the alkene as follows. So first reaction is your ozonolysis. In this, alkenes of following types when treated with ozone, then there is a yield of ozonides, and this on subsequent treatment with H2O and zinc dust yield ketone. So here alkene following this, these are the different types of alkene that are present, that R1 and R2 are attached to one carbon and the R3 is attached to another carbon, and one hydrogen is attached. Secondly, in this you can see a R1 and R1 are attached to carbon and R2 is attached to another carbon, and this all the alkyl groups are different. So these alkynes which are of different types, they are treated with ozone and they are yielding the ozonides, and this subsequent treatment with H2O and zinc, they are yielding the ketone. So here you will see that this alkene, when it is reacting with this ozonide and in the presence of this water and this zinc dust, then there is a formation of this ketone, and the two moles of ketones are formed here. So this reaction is known as ozonolysis, and from ozonolysis is a type of your alkene reactions which are forming ketones from this alkene. Next is your Limix reaction. So in your Limix reaction, an aqueous solution of your sodium iodine oxide and traces of KMNO4 Limix reagent cleavage alkene to its diol and to aldehyde or ketone. So here this is your alkene, and this alkene is treating with this MnO4, that is your magnesium oxide, and this is forming a complex here, and again we are reacting it with the catalyzing it with base, then there is a formation of this alcohol. Dialcohols are formed here, and this solution is then treated with the sodium iodine oxide, and there is a formation of this ketone plus two molecules of ketones are formed here, and in place of KMNO4, we can also use the traces of OSO4, and it prevents further oxidation to acid. So in this, if we are using this OSO4 in place of this KMNO4, then the further oxidation to acids can be prevented. So here in the Limex reagents, an aqueous solution of the sodium IO4 and the traces of KMNO4 are uses, and this reagent is then cleavages the alkene of diol to its aldehyde or ketone. So here you can see aldehyde is also formed and a ketone is also formed. So here you will see this alkene is reacted with this, oxidizes with this MnO4, and after that there is a formation of this complex, and this is base catalyzed, and then there is a formation of this diol, and this diol can be breakdown or can be cleavage with the this Limix reagent, and after that there is a formation of this aldehyde, and this ketone is formed here. Next is your oxidation of 1,2-glycol. So here the following type 1,2-glycols are oxidized by lead tetraacetate. So this is your lead tetraacetate, that is your CH3CO4 Pb, or periodic acid, that is your HiO4 or H5IO6, and there is a formation of this aldehyde and ketone respectively according to structure of glycol. So this this is your glycol, 1,2-glycol. This is the structure of this 1,2-glycol, and this 1,2-glycol, when is reacting with this lead tetraacetate, then or your periodic acid HiO4, or then it is oxidizes to this ketone, and there is a also formation of this formaldehyde is also formed here. Now again the alkyne, the proper alkyl substituted or treatment with water in the presence of dilute H2SO4 or mercuric acetate HgSO4, it gives ketone. So here you will see this alkyne is reacting with the water in the presence of H2SO4, that is a sulfuric acid, that here we are using the dilute sulfuric acid, and the HgSO4, there is a formation of the ketone. You see there is a formation of this alkene. After that this alkene is again reacted, or then it is a reversible reaction, and there is a formation of this ketone. Similarly, other homologies of acetylene on treatment with dicynyl boron followed by oxidation with H2O2 gives ketone. So this homology of acetylene on treatment with this dicynyl boron, that is followed by oxidation with hydrogen peroxide, it gives ketone. So this is your alkene and alkyne, and then it is forming this dicynyl boron SiA2BH, and after that reacting with this peroxide, there is a formation of this alcohol, alkene alcohol, and there is after that again it is reacted and there is a formation of this ketone. Now lithium alkyl on treatment with CO2 gives good yield of ketone. So here lithium alkyl lithium is reacted with the carbon dioxide. There is a formation of this complex, and after that again it is reacting with this alkyl lithium, and there is a formation of again this intermediate is formed and which is hydrolyzed, and there is a formation of this ketone. Similarly with acid also we get ketone. So this is your carboxylic acid, and if we are reacting with this alkyl lithium, then there is a formation of this complex, and then again we are reacting with this alkyl lithium, and there is a formation of this intermediate, and if this intermediate is hydrolyzed, then there is a formation of this ketone. So addition of Grignard reagent to nitrile. So here we are adding the Grignard reagent to our nitrile. So the reaction of Grignard reagent with nitrile forms ketone. So this nitrile is reacting, this nitrile is reacting with this Grignard reagent, and there is a formation of this complex with this Grignard reagent. Then it is hydrolyzed, and there is a formation of this ketone, ammonia, and the Grignard reagent is formed. So this Grignard reagent on MgOx, OHX is formed here. So here you can see this is the nitrile. When it is treating with this Grignard reagent, there is a removal of the this ammonia as well as the MgOH Br, and there is a formation of this complex, and after that they are again reacted, and there is a formation of this ketone. Next is your Wacker process. So alkene on treatment with PdCl2 and CuCl2 gives ketone. So here this alkene is reacting with this palladium Cl2 and H2O cupric chloride, and there is a formation of this ketone. Next is your preparative method of aromatic ketones. So here the aromatic ketones are those compounds which are having a carbonyl appendage on the aromatic structure, to the other side of which one find an alkyl or aryl group like aliphatic ketone. Aromatic ketone can be prepared by various methods. So first is your distillation of mixture of calcium benzoate and acetate yield acetophenone. So here you will take calcium benzoate plus acetate, calcium acetate, and by the reaction of both of them, we are yielding here acetophenone and plus calcium carbonate. Heating of calcium benzoate yield benzophenone. If we are heating alone the calcium benzoate, then there is a formation of this benzophenone. Then this benzophenone is formed here. And plus calcium carbonate is formed here. Next is your Friedel-Crafts acylation. So in your Friedel-Crafts acylation, we are treating the benzene with the acetyl chloride or acetic anhydride in the presence of AnCl3, that is yielding your acetophenone. So here the treatment of benzene with the acetyl chloride or acetic anhydride in the presence of aluminum chloride, that is your Lewis, that is a catalyst, and this is yielding acetophenone. So here benzene is reacting with this CH3, COCl in the presence of this AlCl3. And there is a formation of this acetophenone. Thus acetophenone is formed there. Next, use of benzoyl chloride gives benzophenone. So here the benzene is reacting with this benzoyl chloride, and they in the presence of your AlCl3, and there is a formation of this benzophenone. So benzophenone is formed here. So Friedel-Crafts acylation. In this Friedel-Crafts acylation, we are treating the benzene with the acetyl chloride or acetic anhydride in the presence of your AlCl3, and here we are getting this acetophenone. So this is the structure of your benzene, and which is we are treating it with acetyl chloride, and this we are treating in the presence of your AlCl3, and there is a formation of this acetophenone. So using of benzoyl chloride giving benzophenone. So benzene is reacting with this acid, benzoyl chloride, and there is a formation of this benzophenol. Next is your benzene with carbonyl compound in the presence of AlCl3 gives benzophenol. So here we have taken the two molecules of benzene and sorry. These two molecules of benzene is reacting with this carbonyl chloride and in the presence of your aluminium chloride, and it is giving us benzophenol, and this benzophenol we are getting here plus 2HCl. 2HCl is formed here, and benzene with the carbon tetrachloride in the presence of aluminium chloride that yields dichloro compounds, which on further steam distillation give benzophenol. So here two molecules of benzene with carbon tetrachloride in the presence of aluminium chloride. Here we are forming here a dichloro compound, and after that, after further steam distillation or hydrolysis, here we are getting this benzophenol. Next is the catalytic air oxidation. It is a commercial method. It is a commercial method. It is an industrial method also, from where we can prepare acetophenol, where ethyl benzene. You can see here ethyl benzene is reacting with the oxidation in the presence of treating with oxygen at 126 degrees centigrade under pressure in the presence of manganese acetate. So this is your manganese acetate, and this ethyl benzene is oxidizes in the presence of oxygen at 126 degree centigrade temperature at a heat that is your 126 degree centigrade, and the pressure is also used, and a catalyst is also used, that is a manganese acetate, and there we are getting this acetophenol plus H2O. Next is your Haben-Hosch reaction. So this reaction involves condensation reaction of cyanide with polyhydric phenol and in the presence of a zinc chloride and HCl, which is resulting in the formation of phenolic ketone. And you can see this is a trihydric alcohol, and this polyhydric phenol that is reacting with this methyl cyanide and in the presence of zinc chloride and HCl, there is a formation of this phenolic ketone. So this phenolic ketone is formed here. This reaction is extension of Gutterman and synthesis, and it follows the following sequential mechanism. So this is your triple bond, this is your methyl cyanide, and it is reacting with this HCl. There is a formation of the salt, and again we are reacting in the presence of zinc chloride. There is a formation of this CH3C double bond NH plus ZnCl3. So here you will see this polyhydric alcohol is then reacting with this C double bond NH2, and this is your electrophile, and it is reacting with at the ortho position. So if there is a position, this double bond is formed here. This is giving here a double its electrons, and here it is attached, and this hydrogen is replaced from here, and this is attached simply. And after that, there is a hydronium ion, treating it with hydronium ion, and there is a formation of this this NH is removed from here, NHCH3, and there is a formation of C double bond O CH3. So here NH is removed here, and and uh, and we have replaced this NH from oxygen. So there is a formation of this phenolic ketone is formed here. Then Fry's reagent. So rearrangement. This is when aryl esters are treated with anhydrous AlCl3 at 0 degrees centigrade, then result in the formation of ortho and para acyl derivatives of phenol. So this is your aryl esters, and when we are treating it with aluminum chloride, there is a formation of this ortho and para acyl derivatives of phenols. So next is your this is your ketone, and when we are treating it with the AlCl3, there is a formation of this. There is a formation of this ketone, phenolic ketone is formed here at the ortho and the para position. Next is your Grignard reagent. So this Grignard reagent, aryl magnesium bromide with alkyl cyanide under the nucleophilic addition reaction at carbon of cyanide, which on further hydrolysis with H3O gives the aromatic ketone. So here this is treating it with cyanide, and there is a formation of this ketone acetophenone is formed here, plus NH3 plus MgXOX is formed here. Now, next is from carboxylic acid. So we are passing the vapors of carboxylic acids, except this formic acid, over this magnesium oxide, and we are getting here ketone at 300 degrees centigrade. So this carboxylic acid vapors are passed over the magnesium oxide uh, at the 300 degrees centigrade, and there is a formation of this benzophenone plus H2O plus CO2 is evolved out. Organocadmium compound on reaction with acid chloride forms ketone. So this organocadmium is reacted with this acid chloride and there is a formation of this ketone. And cadmium chloride is also formed. So reaction of cadmium chloride with Grignard reagent give organocadmium compound, and where R is your primary alkyl group or your alkyl group. So these are the questions. So what is the end product of the following sequence of reaction? So here it is C, that is your acetone. Acetophenone is prepared from which reaction? That is the Friedel-Crafts reaction. Compound which give acetone on organolysis is B. Which one of the following compound is prepared in the laboratory from benzene via substitution reaction? That is your acetophenone. Fifth is your ketones can be prepared in one step from which of the following process? That is your hydrolysis of ester, oxidation of primary alcohol, oxidation of secondary alcohol, reduction of reaching reaction of acid halide with alcohol, that is your C, oxidation of secondary alcohol. Ketones are prepared by which of the following main reaction? That is a Clemmensen reaction, Kennesaar reaction, Rosenthal reduction, Oppenauer oxidation, that is a D, Oppenauer oxidation. Isopropyl alcohol on oxidation gives which of the following? That is your acetone. A dry heating of calcium acetate gives which of the following? That is your acetone. Which of the following compounds give a ketone with Grignard reagent? That is your C, methyl cyanide. Propyne on hydrolysis in presence of HCl and HgSO4 gives which of the following? That is your B, that is your acetone. So these are the references from where you can study this topic. And thank you so much for today's talk.